All right, everyone, let's go ahead and get started. We're kind of winding down in the semester. We basically have covered everything so far except our final exam in terms of grades. So I've got homeworks, quizzes, class participation that I take into account, how much you interact or online, if you're submitting your material. We've done 2 exams, and so what's left is the final exam. And there's really about 3 topics that I've covered some of it, and but this is kind of what I need to finish up the course. So I think we did a pretty good job covering polynomial approximations, just fitting curves to data, and what we talked about was minimizing least squares. Last week I talked about curve fitting, and all curve fitting is essentially it's a nonlinear regression. All you're doing for curve fitting is you're just taking your cumulative distribution function, which goes from 0 to 1, and then you're taking your actual empirical data, which is that empirical cumulative distribution function, and you're just subtracting one from the other, taking that vertical distance, and then changing the parameters. Your parameters become your decision variables, and you run it through some type of nonlinear solver, and you just solve what's your best fit. So that's really all curve. Um, I'm sorry, that is curve fitting. I just described curve fitting. Distribution fitting is just curve fitting, but you're just doing it with a distribution. So your distribution is normally, and I don't mean a normal distribution, I'm just saying normally for a distribution, you look at your histogram, but then you turn that histogram into a cumulative distribution, which usually kind of looks like an S or something. So curve fitting and distribution fitting are really one and the same. It's just for distribution fitting, usually you're taking the integral of the the probability density function, and you're fitting that integral function and determining the parameters. So very, very similar. But a lot of times you're not actually taught distribution fitting in statistics. It's just one of those topics that you just kind of gloss over. I mean, I've had a lot of statistics classes in my life. I've taught a lot of statistics classes, and it's just one of those where you just kind of, well, the best fit distribution for this data is whatever, and you're not really taught how to do it. But all it is just a form of curve fitting. One of the things that I didn't cover, that I left out, kind of forgot, was interpolations. And interpolation is really, really simple. You've probably done it. You didn't even know you did it. So I'm going to talk a little bit about that. I posted one chapter from the reference book that I use on interpolation. And he does a pretty good job of explaining what interpolation is. All interpolation really is, and I like to start out kind of when I'm explaining something with just something really simple. So you kind of get it, and then we look at the details of how to do it. Let's suppose that you have, I don't know, this right here, say, is, let me get my pen. Say our response variable right here. And I have this table that shows based on these independent variables, ethylene glycol, freezing point, boiling point, uh, you know, whatever. These could also be my response variables, variables of interest. So, if I have water and I don't have anything in it, just pure water, what temperature does it freeze at? 32. What temperature does it boil at? 212. So that's what these two numbers are, this 32 and this 212. So if I start adding ethylene glycol, which is antifreeze, what impact is that going to have on the freezing point? It's going to lower it. And what impact is it going to have on the boiling point? It's going to raise it. I mean, that's why we have antifreeze, because unfortunately, or actually it's very fortunate, that water is one of the few substances that when it freezes, it gets larger, so the density decreases. Um, Now, it causes problems in a lot of things we do in life because if it freezes, it'll rupture something. So it'll rupture your pipes. It'll rupture an engine block. So I'd say that engineers found that out the hard way years ago. It's like we'll put some water in it and everything's fine, and you come out one winter morning and your engine block is just cracked. Well, so then what do? Well, maybe you add salt or you add something to it. Then that's corrosive, but in general, anything you add to water lowers the freezing point and raises the boiling point. But some substances are better than other. Ethylene glycol is the one that they've used for whatever reason. Probably acts as form of like a lubricant, protects your engine, and probably just has good qualities. So then the question is, if I add 5% ethylene glycol to my water, what is my freezing point now? 29.4, right? So if I add 10%, what's my freezing point? Okay, so now if I add 7%, what's my freezing point? Well, that's interpolation, and it's real easy you could come up with something to figure this out. All you have to do is just have 2 points. You just come over here and you say, all right, this is 5%, this is 10%. At 5%, it is 29.4. At 10%, it is 26.2. And what do? We just draw a straight line between the two. And then you calculate y equals mx plus b. You get your values of m and b. How do you do that? Well, you've got two x's, you got two y's. You just figure that out. So if you want to know 7%, that's all you do. That's called linear interpolation.
So it only works with linear stuff. In this one.
Well, it's a linear interpolation, so it just draws a straight line between 2 points. It doesn't mean the function is linear. Most of the time the function isn't linear. Most of the time. But what you do is you linearize just between those 2 points.
I'll give you a decent approximation.
A decent approximation, okay? So linear interpolation is really, really very simple. You just plug into the formula, and the formula for it, gives, I'm probably not even going to plug it in just because, this is the formula. And all this is just it's just figuring out the equation for the line with 2 points, and then you plug in whatever value of x. So this is the x value that you would actually plug in right here. But y naught and y1, x naught and x1. So the only value you're going to plug in is just x, and then it gives you y sub x. Okay. So that is all there is to linear interpolation. If you want to plug into a formula, there's the formula. You can figure it out yourself. So what he's done is he's actually showed how to do this in Excel and created some functions. And we could create our own function, but why reinvent the wheel? So the first thing we could do is let's just pick a value of 7. I can do a lookup, so I can do like a V lookup. Okay. So V lookup. This is my array of interest. And then I'm going to tell it I want the second column. Oh, no. The lookup value is this guy right here. There we go. So if I plug in like 0, see how it gives me 32? If I plug in 5, see how it gives me 29.4? 10 gives me 26.2. But if I plug in 7, what it does is it just gives me the closest lower number. So even if I plug in like 9, You see how it still gives me the value of 29.4. So that's what a VLOOKUP does. It has to be exact, okay? And if it's not exact, it just picks the lower number of the two, okay? So you could come in and you could actually create a formula using all of these functions here to look these numbers up. And so what you would end up doing is you see like this plus 1 here, G6 plus 1, G6 plus 1. So imagine that if I wanted to find the value of 7, well, what I would do is I would have it find the value of 5, and then I would have it find the value of 10, right? So then I would have these two numbers, these two x's, and then these two y's, and then I would plug into that formula, and then I would then put 7 into it. So you see how you could do something like that, create a formula. And he actually does something like this. He creates what he calls the mega formula, which is up here. Okay, so I mean that's how you would actually do linear interpolation. All right, but who wants to do that? Anybody want to do that? Do you want to do that? I don't want to do that. So you know what he did. You can also use something called a trend function. Is one way of a within Excel. You can use this, and you can look into the details if you're interested. But he created a function called interpolate L for linear interpolation. And all you do is you plug in the value that you're looking up, say right here, and then you plug in your x values and your y values, and you're done. So if I come up here and plug in a value of 10, so you see the answer I get is 26.2. If I plug in 15, what do I get? I get 22.2. But if I plug in a value of 12, it linearly interpolates between 15 and 20. I mean, not 15, 10 and 15. Okay? And you can look at that and say, yeah, that looks, that's about halfway between. Yeah, 24.6 works. Okay? Now, you noticed here he plugged in 61 and we get an error. Well, the reason is if you go outside of those bounds, there's nothing to interpolate. So if I plug in like a value of like 59.5, you know, I get an answer. If I go outside of the bounds, that's called extrapolation. So interpolation is as long as you're in between two bounds. Extrapolation is if you're outside of the bounds. And extrapolation is a whole lot more difficult than interpolation because you're going into the unknown. You don't know. I mean, you know, what happens at some threshold? Does it continue in a linear fashion? Does it curve? Does it all of a sudden just take off the opposite direction? So there's a lot of risk with extrapolation. Extrapolation is really, for the most part, just a form of curve fitting. What you do is try to find a best fit polynomial or some function that, because of your intuition or some theoretical underpinning, that fits the data, and then you just, to extrapolate, you plug into that function. But it's not, the science isn't as well defined, or math isn't as well defined as interpolation, because you've got 2 points, and so you probably know what happens between these 2 points, especially if you have a bunch of points. Now, I mean, in theory, what happens between them could do something really weird and strange, but you're doing the best you can with the data you have. Okay, so we're not going to talk specifically about extrapolation, even though we did when we talked about curve fitting, if that makes sense. Okay. All right, so this is linear interpolation. All right. Now, I think one of the first things that would come to your mind, you know, by talking about interpolation is, well, let's suppose that I have, you know, some data that looks, I don't know, let's suppose my data looks, you know, maybe like this. So linear interpolation is I'm literally just drawing lines between these 2 points. So one of the first things you may want to say is, well, can we not, instead of using just straight lines between the 2 points, could we not do something by, like, say, using curves? And the answer is yes. You can have what's called a quadratic interpolation, to where, if I'm interested in, say, this point right here, instead of just using this point and this point, I'm going to use this point too, or also. And instead of fitting this with a line between the two, I fit it with a curve. Okay? Well, then the question becomes is, well, if my point is right here, do I use this point or should I use this point? I mean, do you use the one before or the one behind? That is called quadratic interpolation. Well, I don't know. Which one should you use? The one in front of or one behind? Well, that's why you don't see quadratic interpolation. It's not that common. What you say is, well, I tell you what, let's just use both of them. So now I have 4 points. So, if 2 points define a line and 3 points define a polynomial order 2 parabola, well, what do you think 4 points define? A function. What kind of function? It's a cubic function, an order 3 function. Okay? And so the next form of interpolation that's very common is what's called cubic interpolation, which is polynomial degree 3. And that's why you go from linear to cubic, because you don't, I mean, I've seen it, but it's just rare that you would see quadratic interpolation. I mean, it can happen, but if it does happen, you have to define the point. You have to pick the 3 points. So you got two of those three. So 2 doesn't evenly fit in 3, but 2 evenly fits in 4. So that's why you have cubic, and you usually just skip quadratic. Okay, and you can look, this is a little more complicated, but all it is just fitting a third order polynomial. That's really it. And somewhere in here, I just saw, there is the formula for cubic interpolation. All right. So, I mean, you would just plug into that. You'd pick your 4 points, and then you would plug in the x value that you were interested in, and it would give you that. I mean, you could, even though it looks kind of nasty, it's not. You would probably make your mistake when you were actually entering your formula in. Is probably where that would happen. But he created a function, and if you're interested, you can actually go in and look at the function that does it. It's not that complicated. Um, but this is what cubic interpolation is. Okay, so if you come down here and you use, say, cubic interpolation, and like linear interpolation, where I plugged in, this is interpolate L. So if I plug in a value of 12, I get 24.6. If I plug in a value of 12 here, I get 24.67. So it's probably a little better estimate. Okay, and then I get an error here where it says extrapolation is not allowed if I go outside of the bound. And the formula for this is just interpolate C for cubic interpolation, but it works the exact same way. All right, so do you understand interpolation? It's actually not that bad. It's pretty simple. Okay. Now I want to talk a little bit about this and how we can use this in the next topic. So I want to continue the topic of distribution fitting. Okay. Did you guys get last week distribution fitting? I mean, does it make sense? Does it make sense to you what's going on?
Yeah, it's not too bad.
It's not bad at all. Okay. All right, so what I'm going to talk about now is kind of the details of distribution fitting and what distributions are the best fit. So if I go in, I finally got my Easy Fit software, hopefully registered. Yep, there we go. And I'm going to take some random data that I created, okay, that I generated from a distribution, and I'm going to plug it into Easy Fit, and then I'm going to go up here under Analyze, and I'm going to fit distributions, and we'll say, all right, here we go, and it fits a bunch of different distributions, all right. So it fits all of these distributions here. Now, the best fitting distribution, it looks to be what's called a Weibull three-parameter distribution. And you may say, what's a Weibull three-parameter? It is what it is. It's a distribution. I mean, they have like 40 some distributions in here. You probably never come across the vast majority of these. So on my desktop computer, I actually only have where I usually fit 5 or 6, like log normal, exponential, a normal, beta, gamma, maybe a wobble. But I don't just do a shotgun approach. That's not actually the best way to do that, because out of 45 distributions, you may get a distribution that just fits through random variation better than the true distribution that it was pulled from. All right. So I just run it just to show you guys. So then the question becomes, well, which is the better fit? So if this is my raw data right here, this is my histogram, you can see as I, pick different distributions, some appear to fit better than others. Does everyone agree with that? So if I hit like a normal doesn't really appear to fit this. This is, looks like it's a wobble, but, probably, I honestly can't remember the distribution I fit. Maybe it was like a gamma distribution, uh, possibly an exponential distribution. So we want to know which distribution fits the best. Well, when we say best, we have to have some metric, okay? So there's 3 different types that it fits. It fits what's called a Kolmogorov-Smirnov distribution, an Anderson-Darling distribution, and a chi-square distribution. And there are debates over which of the 2 is better. I think there's even another one, but I forget what it is. There's several of these. Kolmogorov-Smirnov is popular, and Anderson-Darling is popular. But they both measure different things. So when you look at the actual statistic, you see this is like 0.044, this one's like zero point 0.4, this one's 4.1. This one's 0.046, this one's 7.1, this one's 0.62. So these aren't related to one another. These are actually independent, or if they are correlated, they're kind of loosely correlated. It's not like you can take, say, this number and multiply some multiplying factor to get this number. They're actually measuring different things. So let's talk about the KS. That's what we're going to talk about um, in this class. Because, I mean, honestly, talking about all of these would be a statistics course in of itself, or at least a semester just talking about this. So I'm going to pick what I consider the easier of the 3 to talk about, which is the Kolmogorov-Smirnov test. Okay. Now, these tests are actually, to be honest with you, pretty simple. They're not really complicated in what they do. So here's what I want you to think about. If I just go and I just randomly generate some data, okay, of a certain distribution. Let's suppose that I just go in and I just randomly generate some data that comes from a normal distribution. And I just graph it. The first one I put here, the second one here, the third one here, the fourth one here, something like this. Okay? It's just random data. All right. So, depending on the mean and the variance or standard deviation, let's say variance, I am going to expect certain I'll call parameters from the data that I normally distribute. So for instance, let's suppose that the mean of my population is 50. And let's suppose that the variance of my population is, I don't know, 18. And I just randomly start producing data that's normally distributed from my true population. And I pick 20 data points. And I go in and I calculate the mean of my sample and the standard deviation of my sample. What do you think those numbers are going to be close to? I'll give you a hint. It's on the screen there. Yeah. They're going to be close to 50 and 18 because that is the population that I drew from. So, if I have a population of, let's suppose, I go in and I randomly pick 50 jockeys that ride horses. Okay, their mean and their variance is going to be representative of all the jockeys in the world, or say in the United States. Let's just keep it so you don't have racial differences that may affect height or something like that. But they're going to be representative of that population. So let's suppose that I have a total of 1,000 total jockeys in the country, and I pick 20 of them. Well, it's going to be approximately what the mean and variance of the 1,000 is. But the closer that I get, the closer the sample gets to the population, do you see how it converges? So if I go in and then take the mean and variance of all 1,000, it's going to be the mean and variance of all 1,000 because I have reached the whole population. Does that make sense? All right. So now let's suppose then that, I look at, say, basketball players. Well, do you see how that the mean and the variance of basketball players is going to be different than horse jockeys? Because horse jockeys, you usually want to get smaller people that are light that can ride the horse with a minimal weight. Basketball players, you usually want big, tall people. So my sample is going to be representative of my population. I mean, that's really the goal of statistics, to, instead of looking at entire populations, you don't have to deal with samples. Okay? So I can expect certain parameters from my sample. I can expect them to be certain values. All right? Well, one of the things that I can look at is I could look at not the mean and the standard deviation, but I could look at the deviations from the mean. Okay? And instead of looking at the mean and standard deviation, which requires the calculation of all these points and putting them together, I can just look at the max value. All right? So can you kind of intuit that the max value of different samples will probably be in some range. It will be some expected value. Well, what value will it be? Well, for a normal distribution, on the average, if you normalize it and turn it into standard deviations, 1, 2, 3 standard deviations, this is going to usually be, approximately 3. Well, why will it be approximately 3? Well, because 3 standard deviations encompasses 99.73% of your data. So if I have a sufficiently large sample, my max value from my mean should always be around 3. I mean, every now and then I might get like a 2.8 or I might get like a 3.6, but if it's normally distributed, kind of by definition, that number will be around 3. Does that make sense? Okay. Now that's just for a normal distribution. Now if it's for a beta or a gamma or Weibull or something, it's going to be something else. Well, what will it be? Well, I don't know. It's kind of dependent. So if I have some some random data, okay, and I don't know what distribution that it comes from, but I want to test to see if the distribution that it comes from, say, is normal, right? Well, I can go in and I can look at the theoretical cumulative distribution, which is this red here. You see that? That's what I expect it to be. And then I look at the empirical cumulative distribution function, which is this ECDF, empirical um, cumulative distribution function, where this is just the cumulative distribution function. And if I just observe what the max value is, if my data is truly coming from a normal distribution, that max value on the average shouldn't be further away than a certain number. Does that make sense? And don't worry about what the number is. We don't know that yet. But do you understand that if, okay, let's forget the data that I have. Throw it away. Pretend it doesn't exist. And I say, all right, I want to take a normal distribution with a mean of 15 and a variance of 18, and I'm going to randomly pick 50 points from that and create an empirical distribution. And I'm going to get the max of that. And then I'm going to randomly do 50 more. And I'm going to get the max of that. And then I'm going to randomly do 50 more and get the max of that. And I do that, say, 1,000 times. Do you see how I will create a distribution of what those max values should be, the expected maximum should be? And so then what I do is I bring in my real data and I say, all right, well, what's the max deviation from the real data? Does it fall within the bounds of what these this, these simulations have predicted it to be? Okay, so this is where when I say this is kind of simple, I'll show you. So if you find you look up a table, which has been done, somebody has already created these Kolmogorov-Smirnov tables of critical values. So if I have say a sample of 20, and I say, well, I want to know, say, the 95% confidence, which is 0.05, what is the maximum value, maximum deviation that I can expect based on a sample of 20 with a 95% confidence? And that answer is 0.29407. All right, and so you say, well, where did 0.29407 come from? And what's really interesting, and I think that this I think gives a lot of insights, is it came from back in the 1960s, the guys that come up with this. I mean, you could actually look up where. I could probably look it up now, but I'm not going to. They went in and did exactly what I just described to you. They went in and randomly pulled from certain distributions with certain parameters, and they run it like 1,000 times. And then they literally took the bounds. Like if you want the 5%, you say, well, what is the 950th value when I rank those? And that's where these came from. They did not come from some type of theoretical underpinning. They actually came from computer simulations. So, somewhere down here, let's see, let's see if it's got somewhere down here they show other tables. Yeah, okay. So like right here, this is what this says. And there's another test called the Leah-Force test. And one is if you know your parameters, the other one if you don't know your parameters. But we're not really going to get into the details of that. These numbers are pretty close. Well, they actually kind of measure different things, but that's fine. Don't worry about it. We notice we have table 1 and table 2. So table 1 are the original values that were calculated on a large computer back in the 1960s, and I think they did 1,000 runs to get each one of these values. Later, like maybe back in the 90s, these two other guys, Abdi and Molan, they went in and created new tables. So if you look at this value, this is 0.417, this is 0.4129. And the difference is they ran 10,000 simulations versus 1,000 simulations. And they did that because modern computers are much more powerful. You could go in if you wanted to and run 1,000,000 simulations if you wanted to. But it's just probably going to give you a few more decimal places, and it's all statistics. All right, these values, if it's over 30 or say over 50, these themselves are just approximating functions. So instead of having a table that goes all the way down to infinity, notice what happens to these numbers as you go further down. What do? They start to look like converge, right? So they start to and I don't know this for 100% certainty, but just looking at the numbers, my guess is that your graphs look something like this, where n is going this way. So this starts to linearize out. And so at that point, you're able to then make an extrapolation as to what happens when you get samples, say, over 50, and you plug into these equations. All right. So the question I want to ask, do you understand where these numbers come from? Not necessarily the details of we went in and calculated, but do you have some intuition of where they actually come from? They actually come from computer simulations. And so this is some of the earliest work where they started using computers to, well, it's called bootstrap analysis, where you actually just use the computational power of the computer and kind of forget the theoretical underpinning. Because up until this point, the statistics involved a ton of math, and some of that is some really, really hard math. But when the computer came about, what statisticians realized is, you know what, we may never figure out the closed form of some of these distributions because they're too complex. You can't integrate, say, in a closed form. So let's just let the computer run 1,000 or 10,000 or 100,000 times, and let's just see what the answer is. Okay? So that's where these numbers come from. So we're just going to be discussing this is kind of like I said, depending on if the mean and variance are known or unknown, but that's another topic for another day in another class. We're just going to be discussing the very first iteration of the test. And these are called our critical values. So, is it clear, yes or no, where these numbers come from? Yes, okay. All right, so now, then what we're going to do is if I go down here and I look at a normal, okay, we're just going to look at the Kolmogorov-Smirnov test. And so what I need to do is replicate this number and these critical values. And then I will explain where those come from. So first of all, I'm going to explain where these numbers come from. These numbers come from me simply plugging in to the equation that was provided, which is this equation, these equations down here. Because my sample size is 100, so it's over 50. So if I literally plug in using these formulas, you see how I just plug into these formulas here. Control C. I literally get these numbers here. 0.107, 0.107, 0.114. So do you see how these numbers are the same as these numbers? These numbers just come from a table that was run from a simulation 50 years ago. Nothing really complicated about that from a point of view if we're going to use them. The harder number to get is the actual test statistic, which is 0.15923. So how do I get this? Well, it's not as bad as you might think. What I do is I take my data and I sort it. I go from largest to smallest. So I take this data, Control C, Control V, and I just come up here and I go under Data and I sort. So I just get from smallest to largest. All right? All right. Now, that is the data you see right here. But what I did, instead of sorting it, I used this function called small, which just picks the smallest, the nth smallest. So if you put 1, it picks the smallest value. If you put 2, it picks the second smallest value. If you put 3, it picks the third smallest value. But instead of me having to copy and paste and sort each time, I just go from 1 to 100, my data count, and I use this to sort it for me. Small K1 through K100, which is my raw data right here. L1, which is the first smallest, the second smallest, the third smallest. So do you see how that sorts for me? That's all. It's just a sort button, but instead of me having to copy, paste, and sort each time, if I were to come over here and change my data, this would automatically update. Okay. Then I create my empirical um, distribution function. So all I do is I take my data, basically whatever the label is it the first, the second, the third, the fourth one, divided out by my data count, which is 100. Now remember last week when I told you you actually subtract 0.5 from this? Do you remember? And I told you why? Because you take kind of the midpoint. That's the way you're supposed to do it, all right? That's the right way. In the software Easy Fit, and it took me a long time to figure this out, by the way, they don't do that, all right? They just simply go with the rank divided by the data count. Because I'm doing this and I'm getting answers that are very close, but I know that they're not just a rounding error. And I work and work and work and I read and figure it out. And then finally I figure out they're not actually subtracting by zero point 0.5. It's their program, they can do what they want to with it. But you should be subtracting out by zero point 0.5, so you're doing those half measures. But because I want to show you how the numbers line up, I'm not going to do that. But you understand why. I'm doing it simply because I want to be able to replicate the numbers they get. So this is my actual X values, okay? This is my cumulative. So we can see it ranges from, should range from 0 to 1. So if I subtract it out by 0.5, it would range from 0.005 to 0.995. But because they didn't subtract out, it ranges from 0.01 to 1. But this represents my cumulative or probability or cumulative distribution function, which is this guy right here. No, I'm sorry. Okay, I'm sorry. It's this guy right here, because this is this is my actual data here. This is what it is ranked in terms of my cumulative function. So that ranges from 0 to 1. So you can see this is what my true empirical distribution looks like. And then this guy right here is okay, that's what I thought. Yeah. This guy is what, in theory, it should look like. My normal distribution from these values that are ranked right here. Okay. So I should actually be able to just plug in these values. Let me make sure. Yeah. Okay. I kind of had it complicated, but I take the normal distribution of what's in my ranked values, okay, with a mean of the actual mean of the data, standard deviation of the data. So if I click here and here, This is just the average of my data, and this is just the standard deviation of my data. I just calculated it from my raw data. That's all this is, okay? And then here, I just hit true, which means I want the cumulative, okay? So this is my actual theoretical value that should be. This is my orange line there. Do you see that? One is the theoretical curve. The other is the actual curve. And then this is just the absolute value of the difference of the two. Okay? That's all there is to it. And I've got this. I'd hard-coded it first, but all I really have to do is just do it like this. Won't change. All right. So this number represents all of these vertical deviations. Okay? And then this guy right here is just the maximum of that value. 0.15923. So if I go to easy fit, what do I see? 0.15923. That's all there is to it. I mean, that's it. Now what I did is I created my own function that does the KS test. So I just call it norm test. So it fits to see only if a normal distribution fits. And it's really super simple. This is all there is to it. All I do is declare a function, norm test, select the x values I want. I just declare these variables, data count, data mean, data standard deviation, diff, and diff2. Just declare them. Diff2 I start out is equal to 0. Means my difference is 0. Then I just calculate the count, which is x underscore values, this right here, dot count. It just tells me how many x values I have. Data mean, application dot average x values, just gives me the average of these x values. Application dot stdv gives me the standard deviation. Then I say for j equal 1 to data count, which is 1 to 100 for an x loop. Calculate the difference, which is the absolute value of this guy minus this guy, which is this guy right here in the spreadsheet form. All right. Calculate that diff. I say if diff is greater than diff2, which starts out 0, then diff2 equals diff. End. Next j, do it 100 times, norm diff, norm test equals diff2. So all this does is just pick the maximum value in that loop. Well, that's it. That's all your KS test for a normal distribution is. Pretty easy, isn't it? Does it make sense? Not complicated, right? That's it. That's all a KS test is. Now, then you may say, well, why don't you call it KS test? Well, because I lumped everything for one particular distribution. So the distribution that I'm looking at is normal, and a normal distribution has two parameters, mean and standard deviation. So if I wanted to do a beta or a gamma or an exponential, I have to come up with some estimates for the best fit distribution. You see what I mean? It's like, well, how do you do that? It's distribution specific. You may actually have to use a Newton's method or some equation. Some of these distributions have closed form equations, which gets back to what I discussed last week. Remember when I gave you that kind of disclaimer that Easy Fit uses whatever method that requires the minimum computation. Now, I don't agree with that, but it's their program. They get to do what they want to. And that's how they run all their KS tests. So when you go in here and you look at all of these parameters for the beta, the Cauchy, Cauchy, Erlang, exponential, these parameters that they calculate in whatever way they calculate them. They're not necessarily consistent. The only consistency is they feel that how they calculated these parameters use the least computational effort. Do I agree with that? No. I would pick some metric and go with it, but they didn't. So these are the parameters they use. So if you were to create, say, a gamma test or a beta test, instead of just being able to simply calculate your mean and standard deviation, you might have to plug in to some other algorithm, equation, or something that calculated those parameters. But once you got that, then you would be good, right? And so when I plug in, you can see that when I type in norm test, I get 0.159232, which is exactly this value here, doing it kind of the long way using spreadsheet, which is the same value here. All right. So now how do I interpret it? Well, what I do is I ask the question, is this value bigger than my critical values? So if I want to be, I'm going to tell you how to read this. At the 0.2 level, alpha 0.2, which is 80% confidence, I am 80% confident that I can reject the hypothesis, which is, does the hypothesis would be the data does not come from a normal distribution. That's how the statistical hypothesis would be. So that is my null hypothesis. I'm assuming the data, because that's how statistics works, is you assume whatever it is you're trying to prove isn't true, and it's up to you to prove it is true. So it's not like you're innocent until proven guilty. If I come in and I say, I have some new battery type, and it's better than any other battery out there, I don't get to just walk in with that being assumed to be true. Like, I come up with some nickel metal hydride and put a chlorine atom on there somewhere, and it's better than the lithium ions out there. I don't just get to walk into the world and say, mine's the best. No, I have to prove it. So the null hypothesis is mine is not or is no different than what is out there. And I have to do the work to prove, no, it is statistically different. The same is happening with this. That I assume that, how did I say that? We want to reject the null hypothesis, which says, in this particular case, I think I told you that wrong, that it does come from a normal distribution. And I'm able to reject and show that it doesn't come from a normal distribution. So that's what this yes means. So because this value is lower than this critical value, I can reject it and say it does not come from a normal distribution with an 80% confidence. Well, how about with an 85% confidence? Yes. How about with a 90% confidence? Yes. How about with a 95% confidence? Yes. How about with a 99% confidence? No. And the reason why is because the higher the confidence goes up, the further away I have to be from this critical value. So, I mean, 95 is kind of an acceptance. So we would say it doesn't come from normal data, but can I be 99% sure? It's like, I don't know. But 99% is pretty high. I mean, I'm like almost 100% sure it doesn't. So usually if you're 95, or you can pick, I mean, if you can kind of justify why you would pick a value. But in this case, I'm 95% certain, at least 95% certain, that it doesn't come from a normal distribution. So how many percent certain am I? What do you think I am? I'm between 95 and 99, right? Well, how do you think that I would get the actual value based on my table? I would use interpolation. So I would plug in this table and I would simply interpolate and say, I'm probably about 98% certain that it doesn't come from a normal distribution. So what I wanted to do is show you guys interpolation first and then show you, say, an application for interpolation. Now, the only way to actually get the real value is to go in and run a simulation, and that's what modern software does. So what modern, not easy fit, which is modern, but more sophisticated modern software, what it will actually do is it will just go ahead and generate a small part of that table while it is doing the analysis. So a lot of times with more sophisticated software, instead of just giving you this table, it will give you a number of something like 0.0236. So it'll say like, well, you're like 97.7% certain, okay? Because it actually just goes ahead and says, I'll go ahead and run 1,000 simulations of this. It won't take but another microsecond. The user won't even know, and then I'll just report that value. Okay? But that's what's going on underneath the hood. So it's not really that bad, is it?
Not a big deal.
Oh, yeah. Yeah, exactly. So that's why the KS statistic was one of the dominant um, approaches, because when you start looking at like the Anderson-Darling statistic,
Is that the same person from Darlington Fair?
probably, yeah. These two were big players. They did a lot of things. Um, when you look at this statistic, you notice you have this integral in here, and it's squared. So let me tell you what's going on with the Anderson-Darling test. The Anderson-Darling test is doing this. I'm going to assume they're both continuous just to kind of emphasize the point. Your theoretical distribution looks like this. Let's suppose your empirical distribution looked more, I don't know, let's suppose it did something weird like this. I mean, I'm just saying, which it probably wouldn't, but let's suppose it did. Your Anderson-Darling test takes the integral between the two and squares it, which makes sure all of your areas add up. And that's your test statistic for your Anderson-Darling test. So it's a little more sophisticated, a little more in-depth. So when you look at this, that's what it's doing. It's going from negative infinity, positive infinity. It's taking your actual theoretical function, subtracting it from your empirical function, squaring it, and then this is just kind of times a weighting factor maybe. Uh, yeah, you can see when the weighting factor is 1, it becomes this, and uh, and I don't know I'm not an expert on this, but that is the intuition behind the Anderson-Darling test. So it's a little newer test, probably not much newer because a lot was going on during the period of time when these were all being created, but it's just the cumulative area squared. And so but then you have to go in and you have to run simulations also to get those values. Or there may be some theoretical underpinning for it. Honestly, I don't know. I've used it a lot, but I don't really know what the value. You know, um, it's one of those where I know what it's doing and I know how to interpret it. If I really had to, I could go in, I guess, and write a program to do it, but we're not going to do that. I just wanted to cover one of the techniques. You can come up with your own technique. I mean, that's the great thing. Someone's probably already done it, but you can come up with something like let's suppose that my theoretical distribution looks like this. My empirical, distribution. It's not going to look like that because it's got to keep going up. But, you may want to take the tangential distance or something like that. I mean, I'm not saying that would make for a good measure, but that's how you go about publishing papers on this. Is what you do is you take the existing techniques and literature, and then you take yours and maybe run 10 million simulations, and you say which one actually was able to pick the differences out, or which one was more sensitive. And so there's different arguments that the KS is better than the Anderson-Darling, except if you have a lot of data out on the tails or vice versa. But what I found is just pick one and go with it, because it's statistics, and if you get close to that critical value, then you make a judgment call. So it just is the way it is. So for this, I'm able to say this is probably not coming from a normal distribution. If it was kind of close, I would probably say it is coming from a normal distribution, because if I assume normality, then I can use standard statistics. If not, then I have to use some type of parametric statistics, which is more complicated. Okay? All right. Is it clear? Well, that's what I wanted to hear. Okay, so next week I'll come in and kind of finish this up, show you what to do with those parameters once you get them. Are they significant or not? How do we go about doing that? And then I'll go ahead, I'll probably give you a homework maybe this week, and then I'll go ahead and give you the final exam, and we'll try to get this wrapped up pretty early on.
So, what's going on in OR?
What do you mean? Well, hold on just a second.
Oh.
Okay. All right, well, that's all for